Hello dear students, welcome you all for power system operation and control class. Continue with the third module, that is the last part of this one. We will see the implementation of AGC. So you can see in this figure 7.19 which shows the block diagram of the implementation of the AGC. The frequency of the system is um, constantly monitored along with the net interchange. The AC is filtered to and used to determine the delta P reference for all the units on AGC. If AC, that is area control error, is lesser than 0, then increase the generation in that area. If AC is greater than 0, then we need to decrease the generation in that area. So you can see in this figure it is very clearly mentioned that one. Okay, so to use the state variable feedback technique, the states must be accessible in the physical system for the seeing this state space model that we will see in the next one. So before that we will finish this one. See, you can see this figure clearly here. So centrally measured frequency is there, tile and flow and power flows and net interchange is there, then AC is given to filters, there is integrator is there, allocation to plants is there, then P reference units every 5 seconds, other issues like economic dispatch, governor response and energy balance is there. So this is the figure for the implementation of AGC and how to implement AGC. That is what, as AC value is lesser than 0, we need to increase the generation in the area. If AC is greater than 0, then we need to decrease the generation in that particular area. So we will next move to the state space model of the isolated system. State space model on isolated system. The Routh-Hurwitz criterion can be used as they determine the range of parameters for stable operation. The state space model of the system allows the design of controller using all the state variable of the system. So this technique is extremely useful in multivariable systems. So to use this state variable feedback technique, in the states must be accessible in physical system. We will see the state space model first for the isolated system and then for the two area system. So two area system is there in the fourth module. Before that we will see for the isolated system. Okay. So coming to the isolated system, you can see this figure first. So this is the figure of the block diagram of the isolated system with AGC. There is a governor, turbine, generator plus load, group characteristics, integrator, everything is there. This figure you are knowing. Okay. Now from this we can write the S domain equation for this one is equation 1. You can see 1 over 2hs plus d into delta PM of s minus delta PL of s, which is equal to delta omega of s. So we are knowing this one. So rearranging these equations by multiplying the RHS and LHS numerator and denominators, we can write that equation 2, that is delta omega of s into 2hs plus d, which is equal to delta PM of s minus delta PL of s. Or I want to take the only delta omega s terms which is multiplied with s only. So after simplification I will get these things as equation 3. You can see the things in clearly equation 3, where delta omega s is multiplied with the 2hs and all, another one is d is there. So finally I have rearranged the equation as this one. Okay. So we are having the different models. Turbine we are having. What is the turbine model we are having? That is delta PV of s, which is into 1 over 1 plus STTR, which is equal to delta PM of s, that we are knowing for the turbine model. So if you are once again rearranging that one, that is 1 plus STTR into delta PM of s, which is equal to delta PV of s. Or rearranging the equations, we are going to get that one as equation 6, that is s into delta PM of s, which is equal to minus 1 over TTR delta PM of s plus 1 over TTR delta PV of s. Okay, just shuffling the equations, that's what. Same thing for the governor model. We are having delta P reference minus 1 over R and delta omega of s into 1 over 1 plus STG, which is equal to delta PV of s. Or rearranging that equation, we will get it as equation 8. Okay, you can read out that equation. Okay, so same thing for the integrator model. Okay, see in equation 9, once again finally it is reshuffled to get the s into delta PV of s. Okay, then integrator model is concerned, that is delta p reference of s is equal to minus k1 by s into delta omega of s or that S is taken to the numerator from the RHS side. S delta P reference of S is equal to minus K1 into delta omega of S. So all these equations from starting from equation number 3 to equation number 11 are required for the state equations. So we can define the state variable as, or state variable vector in the time domain as, x is equal to delta omega, delta pm, delta pv, delta p reference, total that matrix is transpose. Okay, that is the state equation x in time domain. And external input as delta pl. Now the state equation can be transferred into time domain and written in the matrix form as this. You can see that is delta omega dot, delta pm dot, delta pv dot, delta pl dot, which is equal to the another matrix with the different values. You can see that one in the previous equations from the 3 to 11 you are seeing that many things are there. That is multiplied with delta omega, delta pm, delta pv, delta p reference, that is the transpose of that vector, plus delta pl is a external input, that is only thing which is having with minus 1 by 2h, that is there in your the first case only, PL, no other, that is the Esteban equation of the ages is there. In turbine model, governor model, integrator model, that delta PL will not come. Okay, so this is what the equation 13, you can consider it as the standard, this is the state equation in time domain. Now we will see the standard form of the state space model is, that is xt of dash dot is equal to a xt plus b of ut, y of t is equal to c x of t plus d u of t, where x of t is the state vector, u of t is the input vector, y of t is the output vector. So that equation for 14 we can write here x of t is comparing with the 13 and 14 now. So I can write x of t is nothing but here delta omega, delta pm, delta pv, delta pv reference transpose, u of t is nothing but delta pl, and y of t is delta omega. Fine. So if we are having this one, so we will come to know that the first matrix which is there in there, that is matrix 1 minus d by 2h, 1 over 2h, like that many things are there, that will be considered as A, and B is nothing but the equation which is multiplied to delta PL, that we can write minus 1 over 2h, and remaining 0 0 what matrix is there, that is as B, and C as 1, because here C is multiplied to the x of t, so that's what we can consider it as 1, and d as 0 because d is multiplied to u of t, so we can consider d as 0. So this is regarding the state space model of a isolated system. Then coming to the pole placement design, the coefficient matrix A determines the stability of the system. For the system to be stable in eigenvalues of matrix A should be lie on the LHS of the S plane. We can design the controller so as to place the poles on LHS further away from the imaginary axis. So consider the control system shown in this figure. You can see the figure 2 for the pole placement design. So you can see these things where u of t, r of t, y of t, k1, k2, kn, many things are there. That is for the pole placement design. Okay. So here we assume the external input r of t is to be 0. The state feedback control is given by u of t is equal to minus of k x of t, that is taken as equation 15, where k is an 1 into n vector, that is 1 cross n vector, that is for feedback gains. This would returns all the state variables to 0 when they have been perturbed. So equation 15 becomes now xt dot is equal to axt then plus b into minus of k x of t, which is equal to a minus b k into x of t, which is equal to a f b into x of t. So that is considered as equation 16, where a f b is the coefficient of the matrix with the feedback, that is f b is for the feedback, suffix f b for the feedback, and characteristics equation for the above state model is given by si minus a f b, which is equal to si minus a plus bk, which is equal to 0, as taken as equation 17. So that is given with the easy to analyze if the state equations are written in the standard phase variable canonical form, that is x1 dot to xn dot which is written here. You can see in the this matrix form. By substituting the AB matrices in canonical form, we will get the equation 17 as Si minus A plus Bk, which is equal to S raised to n plus an minus 1 plus kn into Sn minus 1. Like that, it will go till a naught plus k1, which is equal to 0. Suppose that we specify the closed loop pole location, that is minus lambda 1 minus lambda 2 till minus lambda n. Then the desired characteristics is given by dc of s is equal to s plus lambda 1 into s plus lambda 2 till it is s plus lambda n, or we can write s of n plus d n minus 1 s minus 1 till d naught it will be going. That is considered as the equation 19. The design would involve finding the gain matrix K such that the compensated system characteristics equation given by equation 18 is identical to desired the characteristics equation 19. This can be obtained by equating the coefficients of equation 18 and 19. We will get at last this one, a n minus 1 plus kn, which is equal to d n minus 1, implies kn, which is equal to d n minus 1 a n minus 1, or a naught plus k1, which is equal to d naught, which implies k is 1 is equal to d naught minus a naught. Or in general we can write it as ki is equal to di minus 1 minus ai minus 1. This is a generalized equation. So this is the pole placement design. So by this your module 3 finishes. So this is just a derivative type. So once again you go through these equations and all, try to understand the concept. If you find any difficulties, you can ask me. In the next class we will start with the module 4, that is the state space model for the 2 area system. Okay, fine. So if you find any difficulties, you can ask me. So read these things. By this your third module is finished.